Welcome back to my channel. In this tutorial video, we'll discuss the basics of current, electricity. In the introductory video to electricity, we discussed that there are two types of electricity. That is static electricity, where charges are stationary, and current electricity, where charges are moving. Now, the rate of flow of charges in a circuit is called current. So current is given by the symbol I is equal to charge given by the symbol Q over time. So this is the definition for current, the rate of flow of charge in the circuit. Another common term under current electricity is voltage or potential difference. Potential difference can be defined as the energy required to move a charge through a conductor, or the energy required to move a charge from one point to another in a circuit, or the work done in moving a charge from one point to another. That is work done per charge. And now, as these charges are moving in the conductor, they face an opposition, okay, and there is something that drag them backward if they are moving forward. So the opposition to the flow of charge, which is current in this case in a circuit, is what we call resistance. So resistance is another common term under current electricity. The other common term under current electricity is power. While in general, under work, energy and power, okay, that topic is common in every physics course. So under work, energy and power, we know that power is defined as the rate of doing work or the rate at which energy is transferred. So using that definition, we can derive the formula for electric power. Now, using the formula for voltage here, if we make energy the subject here, we'll have energy E is equals to voltage times charge. Or if we use the other formula here, then we'll have work is equal to potential difference times charge. Then substituting for energy or work in the formula for power here, so where there is W, work, we substitute this, or which is equivalent to this, then we will have power. Okay, so let me write it here. So we will have power, which is equal to W over T, that is work over time. Then for W, or for energy, we substitute this. So we have Q times V. Now we can also write this as Q over T times V. But what is Q over T? Well, that's the definition for current. So we can replace Q over T, which is current here. Okay, we can substitute this by replacing it with I. And then the formula for electrical power becomes this: power is equal to current times voltage. Well, how is now current related to voltage and resistance in a circuit? So we can relate current and voltage and the resistance using Ohm's law. So Ohm's law states that the current through the conductor is directly proportional to the potential difference across 2 points of the conductor, provided the resistance remains constant, because resistance changes with temperature. So in this case, we can also say current is directly proportional to the voltage across 2 points of the conductor, provided the temperature remains the same. Now, using that definition, which is Ohm's law, we can rewrite the formula for power as this. How do we do that? Okay, so we have V is equal to I times R. Now replacing for V, where there is V in the formula for power, we substitute this. What is it that we are going to have? We will have I times R. That makes I squared times R. That is also another formula for power. Or we can make R the subject, or we can make I the subject here in the Ohm's law formula, and we play with the formula for power. Let's say we make I the subject. If we make I the subject, we'll have the formula for power written like that, because we'll have to substitute where there is I, we substitute it with V over R, and that will make V squared over R. So that is another formula for power. Now, how are resistors connected in a circuit? Resistors can be connected in two ways in a circuit. We can connect resistors in series, or we can connect resistors in parallel. Just a reminder, if this is your first time watching my tutorial videos, please subscribe to my channel and leave me a comment there. Or if this is your second time or third time watching my video but you haven't subscribed, please subscribe to my channel and invite others to do so that we can continue together. I just mentioned that resistors can be connected either in series or in parallel. Now let us look at a series circuit. I'll give you some basic hints that you need to follow when you are solving problems that involves resistors connected in series. So that implies resistors connected in series. That implies resistors are connected linearly, like in a straight line, okay, together with the voltage source or the battery here, just like I've drawn it here. Okay, don't mind V3, V1, V2, or the A there. So this A here is connected also in series. It is the symbol for an ammeter. So this that I've put here is an ammeter, which is an instrument used to measure current. Then voltage is measured in volts by a voltmeter, and it is connected across the resistor, just like I've shown it here. Same applies here. Okay, so this implies this voltmeter here will measure the voltage across resistor 1. This will measure the voltage across resistor 2. This will measure the voltage across resistor 3. And this ammeter here will measure the total current in the circuit, because this current is the same current that is passing through resistor 1, resistor 2, and resistor 3. And the voltage VT here, implying total voltage here, is the voltage supplied by the power source. Okay. Now, what are some basic hints that you need to follow when solving problems on series circuit? 1, you should note that the total current through the circuit is the same current that is passing through resistor 1, resistor 2, resistor 3. If there is resistor 4, also resistor 5, all the resistors that are connected in series, the current will be the same. So here, IT implies total current through the circuit, then I1 implies current through resistor 1, I2 implies current through resistor 2, and I3 implies current through resistor 3, and this current is the same. So you have to take note of that. How about the voltage drop? For resistors connected in series, the voltage drop is not the same for the resistors that are connected in series. The voltage drop is different For example, here the voltage drop might be 0.5 depending on the resistor. Here the voltage drop might be 1. Here the voltage drop might be 10 depending on the size of the resistor, which implies that the voltage drop 1 or the voltage across resistor 1 is not equal to the voltage across resistor 2, and it is not equal to the voltage across resistor 3. If the resistors 1, 2 and 3 are not the same, if they are equal, then even the voltage drop will be equal. Now Vt is the voltage or the total voltage of this circuit here. This total voltage is the combination of the voltage across resistor 1, the voltage across resistor 2, and voltage across resistor 3. Now to find the total resistance of the circuit, we combine, or we just add the resistors R1 plus R2 plus R3 plus R4 plus R5. Okay, you add all the resistors that are connected in series to get the combined resistance. Now, how is the total resistance of the circuit related to the total resistance of the circuit and the total current of the circuit? Well, we can relate these three using Ohm's law. That means the total voltage is equal to the total current times the total resistance. Also, applying the same Ohm's law, if we want to know the voltage drop across resistor 1, we will have to multiply the current through resistor 1 and the resistor 1. Okay, but the current one, okay, from this first statement here is equivalent to the total current. So that is equivalent to total current times resistor 1. Okay, that also apply to voltage 2 and voltage 3. So here is an example. Suppose resistor 1 is 5 ohms, resistor 2 is 5 ohms, and resistor 3 is 10 ohms, and the total current through the circuit is 2 amps. What will be the total voltage across all these resistors? That is Vt. How do we compute for Vt, or total voltage, okay, as applied by the battery there? So using Ohm's law, that is Vt is equals to It, or I1, because It in this case is equivalent to I1. So that is Vt times RT, total current times total resistance. But first we have to compute for the total resistance by adding them. Since there are 3, we have 5 plus 5 plus 10, that will give us 20. Now substituting, we have total current It here is 2, then the total resistance is 20, that will give us total voltage of 40. How about the voltage across the 5 ohms resistor? The first one here, okay, that will imply V1. And how do we compute for V1? That is current 1 times resistor 1. But current 1 is equivalent to the total current in the circuit, that is 2. And the resistor 1, that is 5. So that will be 2 times 5. This will give us the voltage drop of 10. How about voltage across resistor 2? Since this is also 5, that means the voltage across resistor 2 will also be 10 if you compute. Now look at resistor 3. Resistor 3 is bigger than resistor 1 and resistor 2. So you can solve for this here, for voltage 3 here, by just, since you know that you know the total voltage, so you can also say this is 40 is the total voltage. Then you add all the voltages, that will be 10 for across resistor 1 and 10 across resistor 2. plus voltage 3 which you are solving for. Okay, this implies you want to use this hint here. Okay, so if that's the case, then what is it that you have? You have 20, or you can just say current 3, which is also the total current times resistor 3. That will also give you 20. Okay, if you want to prove that, you can add all the voltage drops now. Okay, assuming that you did not use this. Okay, you just want to use this. But if you want to get the proof, then now you can add all the voltages to see if you will get 40, which we said is the total voltage of the circuit. So that's how you handle problems that involves resistors that are connected in series. How about problems that involves resistors that are connected in parallel? So we can also come up with some hints that will help us solve problems that involves resistors that are connected in parallel. So resistors connected in parallel implies that as the current is moving, or yes, moving through the circuit, there is a point where the current is dividing. Okay, as shown here. So if this is the current, the total current through the circuit, at this point there is a junction and current is dividing. Okay, some is going this side and some is going this side. Like this, we can say resistors are connected in parallel. Okay, we can disconnect one resistor here and the other resistor will remain connected. But in series, if one resistor gets disconnected, okay, the whole circuit will go off. Unlike that one, parallel circuits are a bit better as compared to series circuits, because one component can be disconnected and the other components will still be working. Okay. Now, if you check this point here, it's like we've connected this point to the positive terminal here, and this point here we've connected the two wires to the same terminal here. Implies that this terminal and this point here and that point are at the same potential. This point and this point here are also at the same potential. So for the resistors that are connected in parallel, the potential difference across resistor 1 here and the potential difference across resistor 2 here is the same as the potential difference across the battery. So the total voltage there is the same as voltage across resistor 1 and voltage across resistor 2. So that is different from the resistors that are connected in series. Okay. As for current 1 is not equal to current 2, and it is not equal to total current. Okay, because current total here will always be greater than current 1 and current 2, because it is the same current that is dividing. Now current 2 and current 3 depends on the size of the resistors. So these three currents are not the same. Okay, this I've explained this one here, which is the total current is the sum of the current 1 and current 2. Now how do we find the combined resistance for the resistors that are connected in parallel? Well, we use this formula here. 1 over total resistance is equal to 1 over resistor 1 plus 1 over resistor 2 plus 1 over resistor 3 plus 1 over resistor 4 for all the resistors that are connected in parallel. And how do you tell that they are connected in parallel? You check the terminals here. Are they on the same potential? Like this one, this cable and this cable are connected to the same terminal here, the positive terminal, implying that they are at the same potential. So after that, we make the right hand side there a single fraction, and then later we make RT, or the total resistance, the subject of the formula. That will give us the combined resistance. Now for two resistors that are connected in parallel, that is simple. If you just do what I've said, then you get this here, R1 times R2 over R1 plus R2. That will give you the total resistance for only two resistors. That applies only to two resistors that are connected in parallel. Similarly, if you want to get the total voltage, we multiply total current times total resistance. Then if you want to get the voltage across one resistor, you multiply the current through that resistor times the resistor itself. So this here should be 1, not resistor 2. So this here should be resistor 1. And similarly, voltage 2 will be current 2 times the resistor 2. In the next video, we will solve some problems that involves parallel circuits and the combination of resistors, some connected in series and some connected in parallel. See you in the next video. Just make sure that you've subscribed so that when I post the next video, you are updated. Thank you.